Welcome to Next Gen Manufacturing Nexus, where we pull back the curtain on the incredible engineering that makes our world tick. Today, we're talking about the invisible architects who stop our most critical systems from literally melting down.
So let me ask you a question. Think about those places where there is absolutely zero room for error. A massive data center crunching millions of dollars in transactions, a live broadcast going out to the entire world, or a surgeon mid-operation. What's the one invisible threat that could bring it all crashing down?
Yep, it's the air, the temperature, the humidity, even how clean it is. If any of that is off by just a tiny fraction, servers will overheat, that sensitive broadcast gear will fail, and sterile environments, well, they won't be sterile anymore. The very air we breathe can become the enemy.
So, who are the people that tame this invisible threat? They are the unsung heroes, the unseen architects of our modern lives. Heating, ventilation, and air conditioning engineers, or as we all know them, HVAC engineers. They literally design the environments that make our high-tech world possible.
Think about it. Their work is the silent backbone of everything. Without their super precise calculations, the semiconductors in your phone couldn't be made. Data centers, they'd just go dark, and hospitals wouldn't be able to keep their operating rooms safe. They are the life support system for technology itself.
Okay, so how in the world do they do it? Well, it's basically a constant battle against the laws of physics. And it all starts with one core concept that, honestly, might surprise you. And here it is, the crucial difference. Heat gain is not the same thing as cooling load. Heat gain, that's all the raw energy pouring into a space from, the sun, lights, everything. But the cooling load, that's the actual work the AC system has to do to fight it. And they are not the same number. Getting that difference right is everything.
So why are they different? It's because of something called the heat storage effect. A building's walls, the floor, even the furniture, they act like thermal batteries. They soak up heat all day and then release it slowly over time. This creates a time lag, so the sun might be at its strongest at noon, but the building might be releasing the most heat at 4 p.m. Engineers have to predict that delay perfectly.
And that heat, it comes from literally everywhere. It's not just the sun, it's the lights over your head, the computers on the desks, and yeah, even us. Every single person in a room is like a little radiator, and an engineer has to account for every single watt of energy coming from every single source.
So, as you can imagine, designing one of these systems is a daily gauntlet. It's this constant high-stakes balancing act between physics, space, and even sound.
First up, the battle for space. In any modern building, every single square foot costs a fortune. You can't just drop a giant piece of machinery in the middle of a high-tech clean room or a fancy office. So the question is, how do you fit these massive, complicated systems into a building that's trying to shrink its footprint? The solution? You have to get in on the ground floor. Engineers now work side by side with architects from day one, weaving the HVAC systems right into the building's DNA. They use really compact modular parts and incredibly clever designs like underfloor air systems to hide all that machinery while getting max performance.
Okay, next problem. The battle against noise. A powerful HVAC system can move a ton of air, but if it sounds like you're standing next to a jet engine, it's completely useless in an office or a quiet hospital. So how do you get all that power without the roar? This is where the science of sound comes into play. We're talking about selecting ultra-quiet equipment, using these specialized mounts that stop vibrations from spreading through the building, and lining all the ductwork with sound-absorbing insulation. The goal is to make the system so effective you forget it's even there. And as one project manager, Fatima, put it, every project presents its own set of complexities. It's a dynamic field that keeps us on our toes. This isn't some cookie-cutter job. Every single day, for every single building, it's a brand new puzzle to solve. So, what kind of tools are they using to solve these crazy puzzles? You can forget that old picture of a mechanic with a wrench. The modern HVAC engineer's toolkit, it's all digital. Seriously, the most powerful tool in their entire arsenal isn't something you can hold. It's not in a toolbox, it's on a computer. It's incredibly sophisticated software that lets them build, simulate, and perfect an entire system before a single physical part is even ordered. And their digital arsenal is just amazing. They use building information modeling, or BIM, to create this perfect 3D digital twin of the entire building. They run simulations for every single hour of the year to get precise energy calculations. And then they deploy IoT sensors that feed them real-time data to tweak performance on the fly. And the results of using this tech? They're just staggering. A senior mechanical engineer, Lionel Lee, said that by using automation on their BIM platform,
His team took a modeling task that used to take 3 weeks and got it done in just 1. I mean, that's a game-changing leap in efficiency.
But this whole digital revolution, it isn't just about working faster. It's about working smarter. And it's put HVAC engineers right on the front lines of designing a much more sustainable future for all of us.
And believe me, the stakes could not be higher. Just look at this number. Buildings are responsible for nearly 40% of all global energy use. And HVAC systems, they are a massive piece of that pie. So every little bit of efficiency an engineer can squeeze out has a huge positive impact on the planet.
And this is exactly where the industry is pushing. We're seeing this huge shift to refrigerants that don't harm the climate, smarter controls that can actually predict what a building needs, a massive new focus on indoor air quality, and really innovative hybrid systems. The whole field is just evolving at lightning speed. So all of this comes together in this new, modern design process. It kicks off with that early collaboration with the architects, then moves into deep digital modeling to make sure nothing clashes. From there, it's countless energy simulations, and the end result is a system that isn't just built for today, but is actually future-proofed for whatever comes next.
So the next time you walk into a building and it feels just perfect, take a second to think about those unseen architects, because the next generation of smart, sustainable, high-tech buildings are on the drawing board right now. Which really makes you wonder, who will be the ones to engineer the very air we breathe inside them?